Hello, everyone. We had some technical difficulties this morning and again this afternoon with regards to Zoom and internet bandwidth, basically. And we were having some issues where my audio wasn't coming through and my video was spotty at best. So hopefully by recording this locally through Zoom and to my own hard drive, I'll be able to get a decent video with good audio quality. Anyways, we're supposed to talk about conservation of momentum. That's what chapter 9 is about. But in the chapter 9, we also cover center of mass, and that's because the Newton's second law says the total force acting on a system is equal to, and that's the net force is another word for it, it's equal to the instantaneous rate of change of momentum of the system. And by saying system as opposed to just a point object, then you can consider, many bodies all acting and interacting together. The disadvantage being that when you treat a system as one big system, then you can't tell forces between the individual parts. Whereas if you broke the system up into individual parts, then you could calculate forces that they apply to each other, because those forces would then be external forces. But one of the nice things about doing it as a system is you can sort of see that by calculating the center of mass, and if the center of mass of the system has initial velocity of 0, then it's never going to move. Its velocity will always be 0, and therefore the center of mass is not going to change. The reconfiguration of putting one thing here and another thing somewhere else, that can definitely change. So I thought I'd work a problem showing you that type of scenario. And believe it or not, if you look on my YouTube channel, you'll also see another one where I did one showing you that that is exactly equivalent to conservation of momentum. So for instance, look on my YouTube channel and you'll find a video about a train car with a cannon in it, firing a cannonball from one end to the other. Of course, the recoil of the train car and cannon is going to cause the train car and cannon to roll backwards as the cannonball fires this way. And then the cannonball is going to hit the other side. That recoil is going to cause the cannon and cannonball, or the car and cannonball, to stop, as well as the cannon itself, and it'll fall ideally straight down. And after doing that several times, you'll end up getting a pile of balls over here, where before it was a pile of balls here and a cannon here. So you can either calculate where that, after a series of say 10, 20, 30 balls are fired, you can figure out where the center of mass is now. And since they haven't changed, you can tell how much the train car's moved. Or you can do that by recoil velocity, see how fast it's moving in each little spot, allow it to travel at that speed for that duration of time it takes for the cannonball to get from the cannon to the wall. And lo and behold, you end up finding out that the exact same motion is predicted. So that's a really nice problem. I highly recommend you look at it. It's really neatly worked out. In this case, I'm going to do something similar. I'm going to solve a problem where two people are in a boat. One's basically a lot heavier than the other, and the boat is lighter than both of them. And what we're going to do is determine basically how far the boat moves by the big person walking one way and the smaller person walking the other way. So let me turn on the document cam and we'll start. So what we have here is what I'm going to treat as a canoe, which maybe looks like this. And I'm going to use really nice little numbers, make life kind of easy. And in fact, I'm going to say that one person is right here, and they have a mass little m, and that little m has is 80.0 kilograms. I'm even going to put the center of my coordinate system right at the location at which that person's standing in the boat. And the x-axis, of course, will be over here. And then I'll go over here at 3.00 meters, and that's going to be where the other person's standing. And the other person has a mass, big M, that's 120.0 kilograms. And then right here at 1.50 meters is going to be the mass of the canoe, which is M canoe equals 70.0 kilograms. So initially, as you can tell in the drawing here, the canoe's just sitting still. There's an 80 kilogram person at one end. There's a 120 kilogram person at the other end. And what's going to happen is this person is going to walk to the other end, and then this person is going to walk back to this end. In other words, you're just going to trade spots. When that's all said and done, the net force acting on the system is 0. Therefore, the center of mass can't move and shouldn't have moved. So the center of mass should be in the exact same spot. So doing so, we're going to use that to find out how far the canoe actually moves during this process. So what I'll do is I'll draw another coordinate system directly below it, and I'll show the final product. And what I'm going to assume is since the 80 kilogram person is going to move this way, that's going to force the boat and the canoe to sort of move this way, but the 120 kilogram person moving this way is going to force the boat and canoe to move that way. And believe it or not, it doesn't matter if you know off the top of your head which way is going to win. If you get the wrong answer, it will tell you by you getting doing what I'm doing, but the answer will come out to be, say, negative. So let me show you, for example, because this person is 120 and this is 80 and 70, I'm thinking maybe this person has a bigger effect than this person. So this person moving this way would make me think the canoe is going to move that way. Net motion would be that way. But instead of even thinking about that, what I'm going to assume is that the canoe actually moves to the left. So here's my canoe now. And in fact, now what we have is what was 3 meters now has this person, which is the 80 kilogram person, at a position of 3.00 meters minus X. In other words, I'm assuming that the canoe in toto moved a distance X. So 3 meters is where they were, and now the person's at 3 meters minus X. Of course, the canoe, which is 70.0 kilograms, that's now at a position of 1.5 meters minus X. And the person that is 120, they are now at a distance of 0 minus X. Okay, so that's actually that coordinate right there is 0 minus X. So what I'm going to do is I'll say XCM is not going to change. So I'll write XCM. And in the first case, I'm going to write 80.0 kilograms times 0.00 meters plus 70.0 kilograms times 1.50 meters plus 120.0 kilograms times 3.00 meters, all that divided by the sum of the masses, which is 80.0 kilograms plus 70.0 kilograms plus 120.0 kilograms. Of course, that also has to equal the center of mass after it. So in this case, I'm now going to have the 80.0, and we'll leave the units off on this one, is going to be at 3 minus 0. I'm also leaving off the sig figs. And the 70 kilograms is going to be now 1.5 minus 0. And the 80 kilograms, or excuse me, the 120 kilograms is now going to be at 0 minus X. Okay. Ooh, I don't know why I said 3 minus 0. Sorry. Glad I caught that now. 1.5 minus X and 3 minus X. Now, all of that, of course, will be divided by that 80.0 plus 70.0 plus 120.0. But since they're equal to each other, I don't even have to take time to calculate that bottom, which, come to find out, due to the math, I'm going to be calculating it anyways. So 80 times 0 gives me 0, but 70 times 1.5 gives me 105. So I've got 105. And notice that's 3 sig figs times 3 sig figs. So ultimately, I should just have no decimal places. That's kilograms times meters. 120 times 3 is 360. Again, that's 3 sig figs. So that's 360.0. Again, that decimal place is not a true sig fig. That's why I'm underlining it. All of that's going to be over the sum, which again, I told you is not going to matter. The 80 times 0, of course, is 0. Now, this other one will be 80 times 3, which is 240. Again, 3 sig figs, that gives you 0.0. And of course, that's kilograms times meters. And then the 70 times 1.5, oh, excuse me, 80 times negative x, that'd be negative 80.0x. And then the 70 times 1.5 would be negative 105.0 again. This one actually is 80 with all three sig figs. And then I have a 70, that was supposed to be plus 105. Now I have 70 times negative x, that'd be negative 70.0x. And then 120 times 0 gives me 0, but minus 120x again. All that would be, of course, over that same sum, which is why I told you don't have to do it. 105 plus 360 should be 465. So I get 465.0 kilogram meters on the left-hand side. And I'm going to go ahead and pull the non-x terms to the side. So I'll say minus 240.0 kilograms times meters. And I'll say minus 80.0. Nope, don't do that one. That was the x. I'll say minus 105.0 again, kilograms times meters. And that's the last one without an x in it. So on this side, I'll get negative 80.0x minus 70.0x minus 120.0x again. In this case, remember, you can see now that I'm adding up those masses anyway. So that's what I meant by algebraically speaking. I'm still going to have to do it. Now, if I take 465 minus 240, that should give me 225, and then minus 105, that should be 120. But I'm going to double check with my calculator to make sure I don't make any careless mistakes. 465 minus 240 minus 105. That gives me 120 kilogram meters. And then the other side is going to give you 80 plus 70 plus 120, which is, of course, since they're all negative, that'll be negative 270. And of course, that is kilograms times x. So x is ultimately going to be negative 120.0 kilograms times meters over 270 kilograms. So when I do that, I get negative 0.444. There's my three sig figs. 4 again, meters. So that's the actual answer. Now notice I intentionally chose the wrong direction because I figured it was going to move the other way, but I wanted you to see how if you get the wrong answer, it's not a big deal. It's just going to give you a negative sign. So what this is saying is that in actuality, the whole system would have moved by about 4.44 or 0.44 or 44.4 centimeters to the right, not 44.44 centimeters to the left. So that's one way of doing conservation of momentum. If I'd given you speeds and stuff like that, you could calculate the relative velocity of the speed of the person walking from this end of the boat to the other end of the boat, and then this person walking from this end of the boat to the other end of the boat, and done all this with conservation of momentum, just like I do with the train car problem, and you'd still get the exact same answer. So ultimately, the answer was 44.44 centimeters, and it moved toward the heavier 120.0 kilogram person. So that's a very fairly straightforward conservation, or excuse me, center of mass problem. Hope that helps you. I'm going to stop the video now, put this up as a one video or as a short video, and we'll solve a couple more problems on a couple other videos and post them as well.